Hello everyone. Today we're going to be talking about functorial data migration. So let me share my screen. And rather than attempt to use full screen mode with Google Hangouts, I'm just going to maximize the PDF. So today we're going to cover 4 topics. The functorial data model, which is a data model that's based on category theory. Functorial data migration, which is the use of the functorial data model to migrate data from one schema to another. A prototype software tool called FQL that we've developed to perform functorial data migration, and then I'll talk to you a little bit about Categorical Informatics, the company that is commercializing the FQL tool. So, as I mentioned, the basics of functorial data migration are described using the mathematics of category theory. And category theory, it's an interesting subject, but it's not required to understand this talk or functorial data migration or to use the FQL tool. So I'm just going to give a brief introduction to category theory, kind of gloss over the details, and then dive into the specifics without the use of category theory. So essentially, a category, it's a kind of algebraic structure like a group or a ring or a field, and it's meant to capture algebras of functions, And like groups, rings, and fields, categories have notions of morphisms. They're called functors. So the basic idea in the functorial data model is to capture schemas, instances, schema mappings, pretty much everything using categories and functors. And I should point out that category theory has been instrumental in the design of many programming languages and query languages and proof assistance, and it's kind of taken mathematics by storm since its invention in 1946. So this next slide here has all the formal definitions of what a category and a functor is, but I'm going to skip that for the purposes of this talk. So this slide here, slide 5, is the one-page summary of what the functorial data model is all about. So in the functorial data model, a schema is essentially a finite labeled directed multigraph with a set of path equivalence equations. So in this example here, the graph has nodes, emp for employee, dept for department, and dom for domain. It has labeled edges, manager going from emp to emp, works going from employee to department, secretary going from department to employee, and then first and last names. Also here is 2 path equivalence constraints. They say that an employee's manager must work in the same department as the employee, and a department secretary must also work in that department. So hopefully you can imagine this is a pretty simple database schema with entities and foreign key relationships. Now down here at the bottom in the set of tables, there's an instance on this schema. So each node in the graph above, in this case emp, dept, and dom, corresponds to a table with an ID column. So for example, there are 3 employees, 101, 102, 103, 2 departments. Here they're given meaningless identifiers, Q10, X02. And the columns in the table correspond to the arrows out of the node in the graph. So in particular, if you look at emp, you see manager, there's a column that says who each employee's manager is. So the instances in the functorial data model are just relational instances on the schemas as graphs, as demonstrated here. So in practice, we find that there's usually a distinction between entity sets, for example, employees, and the set of strings, right? An employee ID number may not matter, but the set of strings really does. So we have a convention where rather than just use plain directed labeled multigraphs, we use graphs where some of the edges into DOM, like I was showing before, are actually drawn as open circles, as you see here on the bottom. So the idea is to sort of make this reminiscent of entity relationship attribute diagrams, which you might be familiar with from studying databases. So with that convention in mind, here's the new slide for the Functorial data model. It's a little less verbose. It's the same schema and instance as before. All that's changed is we now see that first and last and department names are attributes that hang off of employee and department rather than edges. The path equations are the same as before, and the instance data is the same as before, but we've removed the DOM table by convention. So there's not much to that. All of this can be formalized using the mathematics of category theory, but really all you have to think of is a particular kind of relational database schema and relational database instance. So that's the Functorial data model. What is Functorial data migration? Well, data migration is the process of transforming data from one schema to live on another schema. So a mapping between schemas, here written F going from S to T, it's called a functor. It is a constraint respecting mapping. It takes the nodes in your source schema S to your nodes in your target schema T, and it takes edges in your source schema S to paths in your target schema T in a way that respects the constraints of the source schema. So the images of the constraints have to be valid in the target schema. So that is a connection between two schemas. You often hear it called a schema mapping and ETL circles. And each functor introduces three adjoint data migration operations. We call them delta, sigma, and pi. And these three operations form the basis of the data transformation capabilities in the Functorial data model, just like select, project, union, difference, and product form the basis in relational algebra. We like to use these three operations because they have a very nice structure. So the formal definition is to define delta along a functor as composition, and then the other two operations as their left and right adjoints. That's a technical definition. So instead, I'm going to give examples on the next few slides. So here is an example of delta, which intuitively corresponds to projection. There are two schemas up at the top written in the boxes. You have the source schema on the left and the target schema on the right. The functor F maps from left to right. It maps the two nodes N1 and N2 into the one node N, and then it copies the attributes straight across. The data transformation that is associated with this delta moves data backwards. It moves it from the schema on the right to the schema on the left. That's somewhat counterintuitive when you first encounter it, but if you look down at an example instance on the page, it should be easy to see what's going on. So you start with an instance on the schema on the right, so one table named N with three columns corresponding to the three attributes, moves to the schema on the left via the delta migration, so that now it has two tables, N1 and N2. And in particular, we see that this operation is a projection. The three columns have been split, projecting off name and salary and projecting off age. And in particular, in this example, you'll notice that the IDs are all distinct in all the tables. There is no correspondence captured by this projection operation because there's no edge between N1 and N2 in the schema. And in just a moment, I'll get to an example where there is an edge. But intuitively, the delta is a projection-like operation. Now, the second of the three operations is called pi. It's a join or product-like operation. So here we have the same schema mapping as before. F goes from the schema on the left to the right. It takes N1 and N2 to N, and then copies all the attributes straight across. The pi migration moves data from left to right. So it goes in the same direction as the schema mapping, and it goes in the opposite direction of the delta. So here at the bottom, you see an example instance. So you have N1 and N2, two separate tables, each with 3 rows with disjoint IDs in this case. And we see that the delta F operation forms the Cartesian product of the 2 tables. So 3 times 3 is 9. There are 9 rows, and then, like there was in delta, there is no correspondence between the IDs in N1 and N2, so this here is completely a product. It's not a join because there is no edge between N1 and N2 in the source schema. Finally, here's an example of the third data migration operation. So same schema mapping as before. F going from left to right, it takes N1 and N2 to N, and it copies the attribute straight across. Sigma goes in the same direction as pi. It copies, or rather migrates data in the same direction as the mapping. So here are the 2 tables as before, N1 and N2 with disjoint IDs. And you see what happens when what the sigma does is it does what you might think of as an outer union. So in general, sigma is an outer union along with a quotient operation, but basically what's happened here is that because N1 and N2 don't have any columns in common, in the result instance you get a bunch of nulls, null 1, no 2, null 3 in your target instance. So finally, what happens if there's an edge from N1 to N2 in the schema on the left? Well, in this case, it turns out the delta, sigma, and pi data migration operators will sometimes behave in exactly the same way. So, for example, suppose we have these 2 N1 and N2 tables on the left as before, but we've added an edge, F, that connects the 2 IDs to each other. So you see that F, which is written right next to the ID column in N2, is a direct connection. When you pi forward or when you sigma forward, that connection is taken into account, and it essentially performs a join. Both the pi and the sigma performs a join. And in the reverse direction, the delta functor, when it does the project, also maintains the correspondence between the 2 columns. So those are some basic examples, just to give you an idea of how expressive these data migration operations can be. Here's an example where you have one schema with a self loop. You have employees and managers, and you have another schema that is just what we're calling here self-managers. So what happens here? Well, delta F moves data from the schema on the right to the schema on the left. It copies self-manager into employee, typo on the slides, and it puts the identity into the manager arrow. So a projection with a trivial function for manager. Pi F does what you might think of as an infinite join. It puts into self-manager exactly those employees who are their own managers. This is not a kind of operation that SQL can handle, for example. And then what does sigma of F do? Well, it migrates from emp into self-manager representatives of the management groups of the employees. That is, equivalence classes of employees modulo the equivalence relation generated by the manager function. So this means if Bill is managed by Sue and Sue is managed by Alice, then there would be one representative of that group placed into self-manager. And this is also, like pi, an operation that cannot be expressed in SQL. So delta, pi, and sigma are quite expressive. So I talked mostly about the functorial data migration operations, delta and sigma and pi, but there are other interesting and useful things you can do with the functorial data model because of its category theoretic foundations that are not delta, sigma, and pi migration. And here's one example. It's something called a pivot, which is where you can convert an instance to a schema and vice versa. So if you look at the two tables on the bottom, you see that this is an instance on the same employee department schema that we've been using earlier. And because schemas are just directed labeled multigraphs, you can convert any instance into a schema as shown here with the schema up at the top. So for example, because 101's first name is Al, in the schema at the top, there's an edge labeled first from 101 to Al. And there's an inverse construction that allows you to take schemas in this form and turn them into instances. So it's easy to pivot data in the functorial data model because of the way we've defined schemas and instances, and this is not a property that you have in the relational model, for example, where you can't always pivot like this. Okay, so just a quick summary of the positives of the functorial data model. So I showed you the data migration operators, which are quite expressive, and the ability to pivot. What else can you do? Well, if you look at schemas, which are to say these directed labeled multigraphs with path equations, then you find that the class of schemas has a lot of structure. So for example, you can add schemas together or union them. You can multiply schemas together. You can exponentiate them. And you find that they have enough structure to interpret the simply typed lambda calculus, which it's a bit esoteric, but just goes to show you that there's a lot of algebraic structure in the class of all schemas. What about instances? Well, pick a schema, which is to say a category C, and think of all the instances on that schema. Those themselves form a category. And like with schemas, you can add it or union instances, you can multiply them and exponentiate them. But you can do other things with a sort of logic-based flavor. So in particular, there are notions of universal and existential quantification that you can do to your instances. And there's enough structure in the class of instances on a schema to interpret all of higher order logic. So again, that's sort of a technical detail, but it goes to show there's a lot of structure that comes out of the functorial data model. At a more practical level, what else is nice about the functorial data model? Well, the notion of schema we just defined builds data integrity constraints in the guise of path equations right into schemas. And there is a way to get constraints that are more expressive than path equalities that we're looking at right now. Another positive is that the data migration operations, the delta, sigma, and pi, they transform databases to databases. And something like SQL, a query takes as input a database and then outputs just a single table. And if you wanted to populate a database instance, a bunch of tables using SQL, you'd have to write a bunch of queries. Not so in the functorial data model. Instances are easy to pivot in the functorial data model. We saw an example of that. And for the technically minded, the sigma data migration operation, it's similar to an algorithm called the chase that comes up in database theory. And but in fact, our sigma operation has better semantics than chase-based systems like Clio that only operate over TGDs. So anyway, I'm going to give a demo of FQL, which is an open source graphical development environment that you can download from our website at cadinf.com. What it does is it takes data migrations of this delta, sigma, pi form, one after another, that the user has written, and it either translates the data migration expressed that way into SQL and executes that against a database using JDBC, that's Java Database Connectivity, or if that migration is not expressible in SQL, which does happen because our data migrations are more expressive, the tool executes the data migration directly, and then, if desired, it will push the data into a relational database for you via JDBC. The FQL tool also goes the other way. It can translate fragments of SQL into FQL and input and output many different data formats, including RDF and JSON. And it includes a nice select from where syntax for writing those queries, which can be translated into SQL. So I am going to pop up the tool. So as you see here, let me maximize this. The tool, it's a Java jar file that you can download from catinf.com. When you run it, which you can do just by double clicking, you have this text editor that pops up. And let me make the text bigger so that it's easier to see in the presentation. This is a comment I wrote here, hello world // it turns green. That should be pretty familiar. And if you look in the upper right, it has a bunch of preloaded examples. And in particular, I'm going to open the employees example because it is very similar to the example we were using on the slides. So this is a schema called S, written in FQL's text format, 2 nodes, employee and department, as in the slides. 3 attributes, first, name, and last, which are string valued. 3 arrows, manager, works in, and secretary. And then 3 equations, which are the same equations as were in the slides, plus 1 more. Here's an instance on schema S. It's called instance I. So you see that for each node, you have a set. So in this case, the set of employees is 101, 102, 103, just like in the slides. And the set of departments is Q10 and X02, just like in the slides. The attributes are listed as functions. So the first name of employee 101 is Alan, first name of employee 102 is Camille, and so forth. And the arrows are also functions specified in this binary pair form as well. When you click the compile button, it thinks for a while, and then it pops up 2 things. It pops up this viewer here, which gives you a graphical view of the schema and the instance. So for example, you can look at the tables for employee by clicking on employee in this graph. You can view the tables directly. You can view RDF output and so forth. Also, the tool emits here at the bottom a bunch of SQL code that it uses to populate the viewer. So the tool emits this code, and if you want, you can set the tool to emit it in a command line mode, so you can use the tool as a compiler. But basically, it emits SQL code. So here, for example, it creates some tables for department and employee and does a bunch of insert intos. It runs these against a JDBC connection. In our case, we've included a SQL execution engine in the jar file that we use, but you can run against Oracle or what have you. It runs the SQL and then it populates the viewer. So what else is in this tool? Well, here is an example of a schema mapping and a functorial data migration like we saw on the slides. So this example here, it's doing the delta data migration from the slides. You have a schema C with 2 nodes, and in this case, it's a little different from the slides. Each node has 3 attributes, first and last name, social security, and salary. There are no edges, no equations. The target schema D has 1 node, T, and 4 attributes, which have different names. They're postfixed with 0, just to disambiguate. And then here is the syntax for specifying a mapping. So in this case, F is a mapping. It takes, recall that a mapping maps from nodes to nodes and edges to edges, or edges to paths rather. In this case, the mapping is pretty simple. The 2 nodes, T1 and T2, go to T, and the attributes copy over, not directly, but at least to their namesake. So for example, T1 last name and T2 last name both go to the 1 last name, and this is a mapping from C to D. So if you recall, delta moves data from the target to the source, so from an instance on D to an instance on C. So this instance here, J, is an instance on D. It has a set for the node T along with the attributes. And then to apply the data migration, you write instance I equals delta F of J. There's other stuff in this file that's not important for this demo. And when you click the compile button, as before, it emits a bunch of SQL that, in this case, implements the desired data transformation. So here's the schema C, here's the schema D, here's the mapping written kind of in a graphical form. The instance J is just one table with 4 columns. And the instance I is 2 tables with projected columns, just like we were showing in the slides. So to conclude the demo, I'll just mention that there's a bunch of examples in here. There's the sigmas and the pi's and examples of that have been provided by users. So in particular, someone loaded a gene ontology into the FQL tool, and it can be visualized using that pivot-like operation, showing this graph here. So anyway, lots of fun stuff you can play with using the FQL tool, and I will get back to the slides and conclude. Oops. Continue. Yes. Okay, so hopefully I've communicated that there are deep connections between the Functorial data model and other data models, including relational, RDF, XML. And this work, which is coming out of MIT in the guise of the categorical informatics startup, has been successfully applied on a data integration scenario that was identified by the National Institute of Standards and Technology, also known as NIST. And NIST is in fact providing the initial funding to spin the technology out of MIT. And we are looking for both academic collaborators on the MIT side, as well as end users, customers, employees, and just generally interested people on the commercial side. And please visit the website catinf.com for more information. There are also partner projects you can check out. Categoricaldata.net hosts a number of category theoretic data management projects, including the FQL tool. And then appliedcategorytheory.org is a little more broad. It is a community hub for people who are interested in applying category theory in the real world. So, thank you for your time.